Okay, so let's keep going. So now we're going to talk about testing the significance of the correlation coefficient, which is R again. So R tells you about the strength and the direction of the linear relationship between X and Y. However, the reliability of a linear model depends on how many data points are in your sample. So you really need to look at your R and your sample size to see the whole picture of what's going on. We perform a hypothesis test of significance of the correlation coefficient to decide whether the linear relationship in the sample data is strong enough to use the model of the relationship in a population. So again, we're taking that where we're looking at a sample and we're going to compare it to the population. And if your sample is really, really small, you probably don't want to compare it to your population. So the sample data that we computed gave us R. So if we have data for the entire population, we could find the population correlation coefficient. But because we only have sample data, we can't calculate the population correlation coefficient. So as we know, R is our estimate because R is our sample, but R is our estimate for the unknown population correlation coefficient. So we refer to the population correlation coefficient as rho, and it really looks like a P. It's a Greek letter. So rho is your population correlation coefficient, and it's unknown. R is your sample correlation coefficient, and it's known. So think about if you put it in your calculator, it's the sample because there's no way you can put a population in your calculator. So a hypothesis test lets us decide whether the value of the population correlation coefficient is close to zero or different from zero. We decide this based on the sample correlation coefficient and the sample size. If the test concludes that the correlation coefficient is significantly different from zero, we say that the correlation coefficient is significant. So our conclusion is that there would be a sufficient evidence to conclude there's a significant linear relationship between X and Y because the correlation coefficient is significantly different from zero. Okay, we're going to do an example because I know this is kind of confusing. Again, what's the conclusion mean? That there's a significant linear relationship between X and Y. We can use the regression line model of between X and Y to estimate our population. If the test concludes that the correlation coefficient is not significantly different from zero, say it's really close to zero, we can say that the correlation coefficient is not significant. So our conclusion is there is insufficient evidence to conclude that there is a significant linear relationship between X and Y because the correlation coefficient is not significantly different from zero. What's that conclusion mean? There is not a significant linear relationship between X and Y. Therefore, we cannot use the regression line to model the linear relationship between X and Y in the population. Kind of confusing, but if you use these last two slides, you'll never need to really memorize it because it's right there for you. All right, so remember, if X is significant and the scatter plot shows a linear trend, the line cannot be used to predict the value of Y for the values of X that are within the domain of observed X value. If it is not significant, or if the scatter plot doesn't show a linear relationship, it can't be used for prediction. So remember, you can use predictions if it's significant, if R is significant and shows a linear trend. If R is significant and the scatter plot shows a linear trend, the line may not be used or reliable for predictions outside the domain of the observed X values in the data set. We talked about this in the last PowerPoint where you had the third exam and final exam data and they ranged between 65 and 75. You can't predict what somebody who made a 50 on that test will get. You can't do it because it's outside the range. Even if the model is beautiful, your R is wonderful and glorious, you can't use it. All right, so let's perform the hypotheses test. For your null, you're just going to put that rho equals zero, remember, or that fancy P equals zero. Your alternative is that rho does not equal zero. But what does this mean in words? So the null is the population correlation coefficient is not significantly different from zero. It means it's pretty close to it. So basically what we're saying is there is not a significant linear relationship between X and Y in the population. So what's the alternative hypothesis say? The population correlation coefficient is significantly different from zero. So it's not close to zero. So that means there is a significant linear relationship between X and Y in the population. Okay, when you draw a conclusion, method one, using the p-value. And again, I'm always for that p-value because we've learned about it in chapter 10, or excuse me, not chapter 10, but in the hypothesis testing chapter, and it makes it a lot easier. So if your p-value is less than your level of significance, you reject your null. And by rejecting your null, you're saying there is sufficient evidence to conclude that there is a significant linear relationship between X and Y because the correlation coefficient is significantly different from zero. But if your p-value is not less than the level of significance, do not reject that null hypothesis. So you're going to conclude there's insufficient evidence to conclude that there is a significant linear relationship between X and Y because the correlation coefficient is not significantly different from zero. So another way is to use a table of critical values. So in the chapter in the textbook, we'll always use this significant level of 5% or alpha equals 0.05. So the 95% critical values of a sample correlation coefficient table can be used to give you a good idea of whether the computed value of R is significant or not. All right, I'm looking at the table right now. In your textbook, in the actual physical copy, it's 662. If you're using the online version, if you'll type in 662, it'll be before or after that because the electronic copy is a little off on the pages. Okay, so you have a table, and what this table does is it shows degrees of freedom in -2, which is your sample size -2, and then it shows your critical values, your plus and your minus. So what you're going to do is you're going to compare your R to the critical values in the table. If R is not between the positive and the negative critical values, the correlation coefficient is significant. If your R is significant, you may want to use the line for prediction. But if it's not between those, you're not going to use the line. Okay, so here again is our testing data. We found all this, okay? So what I'm going to do now is I'm going to use my hypotheses to predict if I can use this regression line to predict my final exam scores. Excuse me, tripping over my words. So the null hypothesis is rho equals 0, and the alternative hypothesis is rho does not equal 0. These are always and forever the same. They'll never change. If you can memorize or write these two down and know where to look, you're good. So, and I put right here, let me go back. I put right there that alpha equals 0.5. That's just a way of me knowing the level of significance. Okay. Using the 95% critical value table for R with the degrees of freedom n -2, because remember I had, 11 data values in my set of data. Don't think of X as an individual set and Y. You've got to think of them as 1 point equals X and Y. So I have 11 X and Y points together. So then 11 minus 2 equals 9. So I'm going to go in the table, like I said, on page 662. And if I go down to number 9, my critical value is 0.602. And I've got to make that a negative and a positive. So what I'm looking for is since 0.6631 is greater than 0.602, R is significant. So that means I'm going to reject my null. So there is sufficient evidence to conclude there's a significant linear relationship between the third exam scores, which is X, and the final exam scores, which is Y, because the correlation coefficient is significantly different from 0. Because R is significant and the scatter plot shows a linear trend, the regression line can be used to predict the final exam scores. A lot of people like using the table, and I agree the table is good. So you find the way that's comfortable for you. Okay. Assumptions and testing the significance of the correlation coefficient. So testing the significance requires that certain assumptions about the data are satisfied. The premise of this test is that the data are a sample of observed points taken from a larger population. We have not examined the entire population because we can't do it. It's just not possible or feasible at this time. We are examining the sample to draw a conclusion about whether the linear relationship that we see between X and Y in the sample data provides strong enough evidence so that we conclude that there's a linear relationship between X and Y in the population. The regression line equation that we calculate from the sample data gives us the best fit line for our particular sample. We want to use this best fit line for the sample as an estimate of the best fit line for the population. Examining the scatter plot and testing the significance of the correlation coefficient helps us determine if we can use it. The assumptions underlying the test of significance are: there is a linear relationship in the population that models the average value of Y for varying values of X. In other words, the expected value of Y for each value lying in the straight line in the population. We don't know the line of best fit for the population. The regression line for the sample is the best way we can indicate this could be the line of best fit for the population. Again, I can't get the population, so I'm using the sample to see if I can put it and estimate my population. The values for any particular X value are normally distributed about the line. This is important in everyday stuff, but not that important in here. But I'm going to show you what I mean. For you to run this test correctly, you have to make sure that your X values are normally distributed. So that implies that there are more Y values scattered closer to the line than further away. Assumption 1 implies that the normal distributions are centered on the line. The means of the normal distributions of Y values lie on the line. The standard deviations of the population Y values about the line are equal for each value of X. In other words, each of these normally distributions of Y values have the same shape and spread about the line. The residual errors are mutually independent. There's no pattern. And the data are produced from a well-designed random sample and randomized experiment. When I took a whole class on regression in grad school, one of the first things I do is I had to run my data to see if it was normally distributed and what my errors look like. So this is what it's talking about. I know those last couple slides, you're like, what are you talking about? But this is what we're seeing, okay? So in A, I'm showing that my data is normally distributed because this is one of my values, this is one of my values, and this is one of my values. So the Y values for each X value are normally distributed about the line with the same standard deviation. For each X value, the mean of the Y values lie on the regression line. The more Y values lie near the line than are scattered further away from the line. So all we're saying is that, like, these are the X values, but look how they're scattered on the Y axes. And do they show a normal distribution? Because there's a center for these where the line is, and the data scatters away from the top. And they're kind of showing you here the shape of it so you can understand.